Good afternoon. Today I'm going to start talking about quantum mechanics. So we are done with relativity and now we are going to start exploring phenomena in quantum mechanics. So the first thing is to do is to talk about light. But before light, which is well known to be a wave, I want to talk about the best known wave, which is the water wave. So let's start with water waves. Suppose I have like a tank of water and if you just, hit the water surface with something like a ruler, you can generate waves. Let's say this is the wavefront, something like that. So what this means is there is an equilibrium surface like this. So this is, if you want h is equal to 0, the height from the equilibrium is 0, and the dark line means you have a amplitude, something like that. Okay? So this is the water wave. And suppose I want to do the double slit experiment with waters. What I can do is I can put these things in front of the water, right? I can just open two slits. And what will happen is the water will come here, and according to so-called Huygens principle, each slit is going to act like a point source, and they are going to radiate waves like this, and there will be another wavefront like that. And you can think about a screen. Suppose I have a screen here, something like that. So this is screen. And now we have to think about two wavefronts coming together at a point on a given point on the screen. So suppose I have one wave coming from here, another wave coming from here, right? Like that. So when they combine there, so there are different possibilities. Because the path they take is not exactly the same, one wave is going to have a shift compared to the other wave. So maybe the first wave is going to be something like that. And the second wave, okay, let's change the color, maybe blue. Maybe the second wave is going to be shifted a little bit, right? For example, if they match perfectly, each amplitude is going to add up, right? Let me shift just a little bit for you to see. And this is going to be maximum amplitude. And if they shift by exactly half a wavelength, which is, something like that, right? If you look at the equilibrium point, so this is the equilibrium point, you can see whenever red is positive, the blue is negative. Whenever blue is positive, red is negative. So this is going to be minimum amplitude. So we call this one constructive interference, and this one is destructive. And you can see every point is going to have a different shift between these two waves. So no phones or no internet device in the class. I think I see some new faces. You can have the computer, but it is supposed to be not connected to internet. You can use tablets but only to take notes. Okay? Yes?
I am working at the same time.
Then you cannot take this class. So if you are taking this class, you have to be here. Any objections? Okay, I believe you are doing, this is our commitment in day one. I trust everybody that you are going to do this. And let's be civilized people. Okay? So this is the case. Then in each point, like for example, this one, let's say this is, let me just draw the intensity on the screen. There will be these like maximum points and minimum points, right? These are like maximum wave amplitude. This is the minimum, this is maximum, and this is minimum, and so on. So basically, waves display interference. Good. Now let's talk about electromagnetism. So consider electric and magnetic fields. And the way we consider electric and magnetic fields is like Maxwell equations, and there are 4 of them. The first one is del dot E is equal to rho over epsilon naught. This is if you want Coulomb's law or maybe Gauss law, whichever you like better. And similarly, you can think about magnetic field, right? Del dot B, but although there is no reason for it, there seems to be no magnetic monopole. And what this means is this is going to be 0. So this is no magnetic monopole. But like the question is, what is the source of magnetic field? The source of magnetic field is current, and we write it like this: del cross B is equal to μ0 J, right? This is if you want Biot-Savart law, or if you want Ampere's law. And lastly, if you consider the curl of B, why not consider the curl of E, right? Del E, and this is known to be empirically del B del T, which is called Faraday's law, or if you want Faraday and Lenz's law. And if there is something like this for the curl of E, depends on the time derivative of B, then why not have the same thing del in the B field? And this one was suggested by Maxwell the first time. Okay? So these are 4 Maxwell equations. And let's consider number 4, and let's take the curl of 4th Maxwell equation. So curl of E is equal to minus del T curl of B. Okay, sorry, this is a little hard to write here. So for this left-hand side, hopefully you all know about vector calculus, and this is del dot E minus del squared E. And by the way, I want to consider this in empty space, which is, there's no charge in the empty space, otherwise it wouldn't be empty space, and there is no current in empty space, right? Then if there is no charge because of the first equation, del dot E must be 0, and on the left hand side del T, del cross B is, okay, J is 0, so there's only this piece, and this piece is going to give us μ0 epsilon 0 del E del T. And if you clean up everything, what you have is, okay, there is like a second derivative in space. And there's like a del E, which is minus nu 0 epsilon 0, del E squared, del T squared. This is second derivative in time. So this is what we call a wave equation, right? Let's write this wave equation in a little bit clean form. Del squared E plus 1 over V squared del E squared del T squared is equal to 0. So this is wave equation. And the V here, V is 1 over mu 0 epsilon naught. And from the wave equation, we know the wave speed, right? This is the wave velocity. And mu 0 is a fundamental constant of nature. Epsilon naught is a fundamental constant of nature. We know what their values are. If you put this thing in and calculate this 1 over root expression, you are going to find 299,792,458. And the unit turns out to be meter per second as we want.
Would you show any more?
Go up.
How did we found 1 over squared?
So I just use Maxwell equations, right? So I just, there's like, you can see there is like some constant. I call this 1 over V squared. I define this 1 over V squared. The reason I call it 1 over V squared, we know wave equation. And in the wave equation, time derivatives comes with wave speed or wave velocity. Any questions or comments? Okay, this result was also first suggested by Maxwell. And he said maybe there is like some kind of wave of electromagnetic radiation. And since the wave speed of this electromagnetic radiation is like this, which is the speed of light, doesn't take a rocket scientist to figure out. Maybe these waves are like light waves. These lights we see, maybe they are actually electromagnetic radiation. And I think this was suggested like late 1800. Any questions or comments so far? So even though it was like a beautiful demonstration, a very nice theory, everything worked just right. So we needed an experimental verification because we are doing physics. Without experimental verification, your theories are only theories. So nobody cares because we have to like benchmark our results by nature. And the proof of this prediction came by Hertz. In I think, again, I don't remember the exact date, but let me call it late 1800s. And he using what we now today call antennas. And that was the end of story. So light is a wave, and there is nothing else to talk about it. Any questions? However, this was not actually the end of the story. In like early 1900, there was a new experiment which was called Blackbody radiation. And let's talk about this just a few minutes. So as you are familiar, like all objects radiate radiation. Of course, right now when I look at you, I see the light that comes from these light bulbs or maybe sun, and that's reflected. So that's the source is actually external, either sun or the bulbs. But if I put you in a dark room, and if I can look at you with, like, say, infrared camera, I would see the radiation coming from your body without any source. And that radiation happens to depend on the temperature of the object, right? And we are also familiar with this. Like, for example, like a hot light bulb glows a little bit like yellowish, and the color changes, right? Or like if you ever like experimented with fire when you were a child, like certain part of flame is blue, certain part is yellow, and we know these like different parts of the flame are different temperatures. So basically, different T means different color, which is different wavelength. Okay? And the problem of blackbody radiation, given the temperature, calculate the amount of light at a given wavelength. Calculate I of lambda, intensity of radiation. And typically, of course, we cannot do this kind of experiment with our like eyes, but if you do the experiment with like some optical spectrometer, what you are going to find is something like this. So this is the intensity. So I can either plot as a function of wavelength, or I can plot it as a function of frequency. Let me choose the frequency here, frequency, and the units at least I use for it is like 10 to the 14 hertz. And if I do this experiment, let me first give you a result for like a, like this is like, for example, T is equal to 1200 Kelvin. And if I increase the temperature, so this is T is equal to 1800 Kelvin. And x-axis is light, or maybe let me call it radiation intensity. And the problem was, why does this blackbody spectrum have this shape? The question is, why is the shape of these curves like that? Okay. So we want to explain that. And now to explain that, we have to make a couple of assumptions. So we first consider like an ideal blackbody. An ideal blackbody, you can think about like a closed box, and you can send light from only a tiny hole, and you can observe light from a tiny hole. So once light enters, I don't know, it just does all these crazy things, and it equilibrates at a temperature which is characteristic of the cavity. And we can think about this. Okay, now you can see like there's like a reflection here and reflection here and reflection here. Basically, these like infinitely hard walls, the light cannot penetrate. What this means is like the amplitude of light when it reaches the wall should be 0, right? Otherwise, it wouldn't be wall. By definition, a wall, right, shouldn't have any light. So what we are going to say is like, suppose we think about like a one-dimensional blackbody like this. And what may happen is like maybe, okay, this is the amplitude, exactly like the amplitude of the water waves we started today. Maybe it's going to be like this, right? These are fixed ends, and this is the light. Maybe it may do something like that. That's also fine. Or maybe it can do something like that. As long as the ends are fixed, this is allowed light mode. So what I'll call this allowed light modes inside cavity. Good. Yes.
So you say the intuition behind Blackbody is the fact that all the light is absorbed and not penetrated.
Yes, yes, right. So there is like a light inside. Like in real life, of course, any given body absorbs and emits light, right? You are, for example, right now absorbing light, you are emitting light. But this is a little bit more complicated, right? We have to have some thermal equilibrium. So the Blackbody assumption says like forget about this emission, like whatever comes in is absorbed, and given the shape of the cavity, what is the statistics of lights, right? Light waves trapped inside the cavity, and what is the resulting like temperature? That's what we are trying to calculate in this problem. Hopefully, which will be clear in a little bit.
John, I don't understand these wave shapes.
Which one?
All of them. Why it only absorbs these shapes?
Why it only absorbs these shapes?
Yes.
I mean, it like I say like okay, this is like an arbitrary shape. I happen to choose like square. It doesn't have to be, but the key about this is like at the walls, radiation intensity should be zero, right? There cannot be any radiation going inside the cavity wall. So what this says is like we have to fit wave in cavity. So that's what we are trying to. Of course, the calculation is we didn't do any calculation yet. We are setting up a problem, and like for example, this one. So if the size of the box is L, for example, this light lambda over 2 is equal to L. Similarly, I can have, let me draw one more, and again, let this be 0. The next is like lambda over 2, right? So this is peak to peak is lambda, but there are two of these is equal to L. Or I can have something like that. I'm basically enumerating a geometrical quantity based on my shape, like lambda over 2 times 3 is L, and so on. And I can have infinitely many of these, right? Like I can have, for example, lambda over 2, 100 also has. All of these waves, which are all different wavelengths and different colors, they are allowed to exist inside the box. That's what we are doing right now.
What would be if an intensity not be zero?
Then like think of like a wall, and suppose you have like a string here, right? Which is exactly the same thing, and you want to put like a mode of wave on this string, and what we require is like the end of points have to be fixed. If the end points are not fixed, you break the wall, right? If you break the wall, then you break your initial assumption, like infinitely penetrable hard walls, then it's not consistent, right?
Pardon?
Yes.
In the graph that you drew, you showed radiation intensity, right?
Yes. So this is the empirical result, right? This one.
Okay, this radiation intensity comes from like that measurement that the Blackbody radiation over the light
Yes.
came inside.
Yes. this is actually a little bit like more complicated, but what happens is like you have an object. Suppose you can heat it at any temperature you want, and you put like a CCD camera. Suppose this is our like optical spectrometer, and this CCD camera can just look at all frequencies or all wavelengths and draw out the intensity. And if the temperature is 1200 Kelvin, in your computer screen you are going to see the blue curve. And if you put a little bit flame and increase the temperature to like 1800 Kelvin, in your computer screen you are going to see a red line. That's what the experiment is like. Good? Yes?
Is there any emission of light?
Of course, in real life there is like both absorption and emission. But this is only going to complicate the problem. Rather than that, we are saying like, okay, in the blackbody problem, let's forget about emission. And let's say like in an ideal, which doesn't exist, right? No such thing exists, but this exercise is going to tell us something about this result. Let's assume there's only absorption. And for absorption to happen, like the light should fit inside the cavity. And this like toy demonstration is what we call blackbody. Okay? So here is the result. So number of modes in frequency nu to nu plus du nu is equal to, we show this by g nu d nu, and this is given by 8 pi divided by c cube nu square. So I promise I will show this later towards the end of this class. So we will derive this, which is not important, but it is a purely geometrical result. And we'll see how to get that. So this is total number of any given frequency, right, has this many modes, which comes from like this calculation. And now there's a second, so this is first requirement, and the second ingredient is what is the average energy per mode mu. So if I have like a frequency nu, what is the corresponding energy for this frequency mu? And to answer that, Rayleigh and Jeans used so-called equipartition theorem. So let's remember what this is. If you didn't know, I'll give you a quick equipartition theorem. It says each degree of freedom contributes 1/2 kT to average energy. Okay, another promise, we'll also see how to do this towards the end. We will drive this too. So that means don't be scared, don't close your eyes and don't run away. Just like listen what this will give us, and eventually we'll see these things. Let me give you a couple of examples. Like a monoatomic gas. There are like 3 degrees of freedom, because there's like x direction, y direction, and z direction, right? Then average energy, let me use this notation, average energy is 3 times 1/2 kT. So this is energy per atom. So another example is, let me not give too many examples, let me just give you 1D harmonic oscillator, there are like 2 degrees of freedom. There's like kinetic energy, like energy either can be in the particle, which is moving, or it can be in the spring, which is the potential energy. Then this one is also E is equal to 2 times 1/2. Okay, this K is KB, this K is KB, T, and KB is Boltzmann constant. For example, for electromagnetic radiation, from last year you probably remember energy intensity of light is proportional to E squared plus B squared. This actually kind of behaves like a harmonic oscillator as well, right? Energy can be electric degrees of freedom or magnetic degrees of freedom. There's also E bar is equal to 2 times 1/2 kBT. Okay, now we can write the results. So let me define U nu, D nu, which is by definition total energy in interval nu to nu plus du nu, and this is okay average energy per mode. Like I'm asking how much energy does each mode contribute times total number of modes, right? And we just, from the equipartition theorem, the first parenthesis is, we know KT. Okay, this is KB times T. And from the first result I showed you, it's like 8 pi over C cube nu square d nu. Okay, so this is then U nu is equal to so this is what we call Rayleigh-Jeans law. Yes?
What do you mean by mode?
So the mode is each frequency, I call it mode. Rather than frequency, I call it mode, right? And the allowed frequencies are constrained because of the geometrical shape. I cannot have an arbitrary frequency because I have to fit it in a box. And each allowed frequency is like, terminology is called mode. Now, if you remember the blackbody radiation, so let's draw one more time. Okay. So this is intensity. This is frequency. And the results we saw was something like that. And the result we see here is, you can see at small frequencies, they both go to 0, which is nice, right? Blackbody empirical result, which is Blake curve, goes to 0. And our derivation of Rayleigh-Jeans law, because of nu squared, it also goes to 0. But as you keep going, this is like a parabolic, right? This is parabolic, and U of nu goes to infinity, whereas this second one, empirical, let me call it U empirical, goes to constant as nu goes to infinity. Okay? We have a catastrophe here, and this is what we call UV catastrophe.
Use what, sir?
Huh?
Use what?
So UV is ultraviolet catastrophe.
Mu.
Mu,
Yeah. Well, what is mu?
mu is the frequency of light, right? Right. I have like, again, I think you should go back to the experiments in our head. We have like an object which has like a geometrical shape, and we have like a camera, and each frequency can be measured by the CCD camera, right? I don't know. There is like some inside diffraction grating, some complicated optical instrument inside. We have no interest, but at the end it gives us the result on the computer screen. And I know at each frequency there's like a corresponding intensity. At a different frequency there's like a corresponding frequency. And now I have two things to compare. One is the intensity coming from Rayleigh-Jeans law. The other is intensity coming from experiment. And these two seem to have like a good agreement at small frequencies, but they are terribly divergent at like large frequencies.
So is this chapter about getting familiar with the concepts? Because too many formulas.
Yes. Like right now, like I think I don't expect you to understand it. I'm like documenting bunch of results that may or may not make sense, but we are going to come over to these things over and over again. For example, this counting modes and like this, how to fit waves in a given, we'll keep doing this a lot, so you are going to understand that. So sometimes we have to be patient and hope for the best. Of course, the easiest thing is just to give up. This is over the top of my head, and you don't have to worry about that in that case either.
No, it just makes
Yeah.
me confused.
So right now, you see, I don't do any derivation, right? Like, I'll give you even more like a beast-like result now to make sense of all of these. So obviously, Rayleigh-Jeans doesn't work, and the way to fix that came due to Max Planck. Here's what he came up with. Like if you want to make sense of these things, for example, make sense of this one, I am going to write. Max Planck came up with 8 pi h over c cube, nu cube divided by exp h nu over kbt minus 1. Right? How do you make sense of something like that? You just wrote this thing, and it turned out to be working perfectly fine. So this is also an important. So this is what we call Planck's formula. And there's only one fitting parameter in this equation, which is h is the only fitting dimensionful parameter. It has a dimension, and which turns out to be Planck's constant. H, you can take any radiation spectrum you want, you can fit this function, and I think everybody here knows how to fit functions to experimental results, and you can pull out what h is, and what you are going to find is 6.626 times 10 to the minus 34, and the unit of h is joules time second, and we'll call this Planck's constant. We can check if this formula is making sense in like high frequency and low frequency limits. Let's check high frequency. Nu goes to infinity. Obviously, there's like a gigantic exponential, so u nu is going to go to 0. So that's a check. And low frequency and h nu over kBt much less than 1 is what I call low frequency regime, and in that case exp h nu over kBt can be approximated at 1 plus h nu over kBt, and there's plus 1 here and minus 1 here that are going to cancel. There's like a nu in the denominator and nu cube in the numerator, and you can see u of nu is proportional to nu square as nu goes to 0, same as Rayleigh-Jeans law. And of course, there was the big job of how to justify something like this, right? You don't pull out functions like this from your pocket and just paste wherever is necessary, right? And Planck thought about this a lot. And I think in his memoirs he said it was like a lucky guesswork, but I think he knew very well statistical mechanics, and he knew very well results of Boltzmann, and he actually did like a very sophisticated guess. It was not from his gut strength that he came up with this. And for this to justify this formula, Planck said energy of each frequency is not kT, like the equipartition theorem says, but it is h times nu, and there's also an integer. So energy is not temperature dependent. Not only it is temperature independent, but also it depends on frequency, and there's also like this integer, which can be 1, 2, 3, ... And the corresponding average energy, so this is, to agree, the average energy is going to be h nu divided by exp h nu over kBt minus 1. You can kind of see, like comparing these two equations, there is like an average n, so let me call it n bar, is something like 1 over exp h nu over kBt minus 1. So we will also derive this formula if you are patient. So let me give some references for like having like an idea of numbers. So for orange light, which is visible, nu is 5.00 times 10 to the 14 hertz. Corresponding energy is h nu, which is, okay, you can put the Planck's constant, which is 6.6 times 10 to minus 34 joule per second. Frequency is this. You are going to find 3.32 times 10 to the minus 19 joules. But it turns out joules is not a good unit of energy for studying quantum mechanics, because we are talking about atoms and electrons, very small quantities, they have very small energy. A better energy is electron volt, EV, is 1 electron times 1 volt, right? You can just convert joule to electron volt. Let me just write the result. This is equal to 2.08 electron volt. And typically we are going to have like an electron volt energy in quantum physics, and this electron volt energy turns out to be huge in atomic world. Okay, let's take a break and continue in the second hour.